Continuing with ellipses. We've been reviewing the key features of an ellipse. What would the equation look like? What's our basic equation for an ellipse? Okay, if it's not at the centered at the origin, what would we have to do? X minus h squared over something. We'll come back to that. And then y minus k squared over something, and it equals 1. Okay. How do we know which one's which on the bottom? What are the two letters that I have to dump in yet? The a and b, right? But they get squared. So one of them is going to be a squared. One of them is going to be b squared, right? But they can flip-flop. So how do I know which one's which? A squared would be the bigger one. Yes, because a is bigger than b. Okay. So our first question here is to prove that this is an ellipse, and then to actually find the key features like the vertices, covertices, and foci. In order to prove that it's an ellipse, we need to get that equation to look like the one we just wrote in blue. Okay? So it's going to require completing the square. When we did this for parabolas, to complete the square, we moved anything that was associated with the squared term. So, for example, if it was an x squared, anything that had x squareds or x's we put on one side, and all the other stuff got moved over to the other. Okay? We want our x squareds and our y squareds on the same side here. Okay? But we are going to rearrange them, regroup them a little bit so we can kind of clump them together. So, in this case, we have a 9x squared and we have a negative 36x. I'm going to put those next to each other because they're both x's. Okay? Then I'm going to clump together anything that has y's on it. So the 25y squared and the 50y are going to get grouped together. And then that constant, I'm going to move out of the way. I'm going to move it to the other side because it's not the number I want to make these perfect. Okay? So I'm going to add that 164 over to the other side. Okay? Now, when you complete the square, in order to do that whole b over 2 squared and figure out what number is missing, you have to have a single x squared or a single y squared. We have 9x squareds and we have 25y squareds. Okay? We can't have that. We need to get that term, that coefficient out of there. So what we're going to do is we're going to factor a 9 out of the two x pieces. Okay? And now I have a 1x squared in that parenthesis. Okay? So I can complete the stuff that's inside the parenthesis and just leave that 9 sitting outside. So I'm going to leave a little space here because I want to figure out that missing term. And I'm going to do the same exact thing to the y pieces. Okay? So what can I factor out of my y's? Okay? So the 25 is going to move out in front of it. I'm going to have a y squared plus 2y. And then I'm going to leave some space because I'm going to complete the square. And I've got 164 on the other end. Are we okay with those first couple steps? Yes? Okay. Now, looking just inside the parentheses, in order to find our first missing term here, we have to take half of negative 4 and square it. So half would be negative 2, squared would be 4. So I'm going to put a 4 in here. And then remember, whatever I do to one side, I have to balance by doing it to the other side. But I did not just add a 4. I really added what? A 36. Because I put that 4 in the parentheses, and there's a 9 that's getting multiplied to it. So I've really added 36 to the left side, which means I have to balance it by adding 36 to the right side. Okay? Doing the same thing for the y's. I need half of my middle term, so half of 2 would be 1, and then square it. 1 squared is 1. So I'm going to write it as a 1 here, but what did I really add? I really added 25, because this 25 gets multiplied over there. So I have to add 25 to balance it out on the other side. Okay? Now, our next step when we complete the square, the whole purpose of doing it is so that we can factor those. those perfect square trinomials. So we end up with 9 times something squared, right? So how does x squared minus 4x plus 4 factor? Okay. And then doing the same thing with our y piece. We have y squared plus 2y plus 1. It's going to factor down into y plus 1 quantity squared. Okay. On the other side, what do I get if I take 164 plus 36 plus 25? Okay. Now, is it looking closer like an ellipse? More like that equation we're used to? What would be my last step that I'd need to do? Yeah, we want to get a 1 on the end, right? So we're going to divide everything by 225. Okay. So my first term, I have a 9 over a 225. What would that fraction reduce to? In other words, how many times does 9 go into 225? 25 times. So I can divide 9 out of the 9 and get 1. And I can divide 9 out of the 225 and get 25. Okay. So what do I do on the next piece? 25 goes into 225 9 times. And on the end, 225 divided by 225 is just 1. Okay? So does it look like an ellipse now? Yes. Now they've asked us to find a few things. They want us to find vertices and foci. I'm also going to say find covertices. Remember yesterday we talked about this textbook doesn't refer to them as covertices, but we are. So I'm going to expect you to find those as well. You can do this by sketching a picture that might help you to figure out where your points need to be. Some of you might be able to do it just doing the arithmetic. Okay, I'm okay either way. In order to find vertices, covertices, and foci, we need to know A, B, and C. What can we take from our equation here? We can find A and B. Okay. What else do we need to know? What? We are going to find the vertex, which is coming from our A piece. But before we can do that, when we measure out our A's and our B's and our C's, we're going from the center, right? Our center's not at 0, 0. Where is our center? Based on our equation, what's our center? 2, negative 1. Okay. So all of our points are going to be going from that. All right. I heard someone say A is 5, right? 25 is bigger than 9. So that's got to be the A squared piece. So A is going to be 5, and it's paired up with X. B is going to be 3, and it's with Y. And then what was the relationship to find C? A squared minus B squared equals C squared. So C is the square root of A squared minus B squared. Okay, A squared was 25. 25 minus B squared was 9. 25 minus 9 is 16, and the square root of 16 is 4. Okay. So here's where you have your choice. If you want to sketch this out, to actually plot your center and move your dots using our A, B's, and C's, you certainly can. If you can do it just by manipulating the center point, I'm okay with that too. I'll show you what I mean. Our A term leads to our vertices, yes? We said that A goes with X. That means we're going to be moving 5 spaces in the X direction from our center. So we are changing the X coordinate of our center. So we're going to take our center point, which was 2, negative 1, okay? But we're going to change that X value by adding and subtracting 5. Okay, so what do we get if we add 5? So we have a vertex at 7, negative 1. And if we subtract 5, 2 minus 5, we'd have another vertex at negative 3, negative 1. We okay with that? All right. Covertices. This comes from our B term, and we said B is moving in the Y direction. So we are going to go from our center point, and we are going to change our Y coordinate now by adding and subtracting 3. which means we have co-vertices at 2, 2, and at 2, -4. Does that make sense? Yes? No? All right. Foci? Foci are going to go the same way the vertices did, right? They're all in line. So going back to our vertices, we were changing our x-coordinate. Okay, so our foci, we're going to be adding and subtracting 4 to our x-coordinate. So we're going to have 2 plus minus 4, comma -1, which gives us what? 6, -1, and -2, -1. Okay, so if you want to do them just algebraically like that, you certainly can. If it helps you to plot them, you can do that as well. All right, I've said all along, having that visual is going to be helpful. Where the problem comes in, and the whole reason I'm showing you this, is when that C value, for example, is not a nice integer. Okay, so let's say C was the square root of 5. You're going to be taking a coordinate and adding and subtracting the square root of 5, right? So it's not going to be something you can simplify down. So you're going to have it looking more like this. Does that make sense? If instead of a 4 we had a square root of 5, you'd leave it as 2 plus minus root 5, comma -1. Okay? All right. Are we okay with completing the square? The most common thing that I've seen students make a mistake on is right in here. All right. When you insert that value, you forget about the number that's out front when you figure out what you're really supposed to be adding over to the other side. Okay, so be real careful of that. Make sure you're really keeping it balanced. All right, we're just going to look at a couple applications. That was our last learning objective for this section on where you might see an ellipsoid used in the real world. Okay. It says, because of their shapes, ellipses are used to make reflectors of sound, light, and other waves. If we rotate an ellipse in the three-dimensional space about its focal axis, the ellipse sweeps out an ellipsoid of revolution. If we place a signal source at one focus of a reflective ellipsoid, the signal will reflect off the elliptical surface to the other focus. So in other words, any signal here is going to bounce off the edge and be aimed at the other focus. Okay? This property is used to make mirrors and for optical equipment, and also to study aircraft noise in wind tunnels. Have you guys heard of a whispering gallery before? Okay. The idea behind a whispering gallery, it says, in architecture, ceilings in the shape of an ellipsoid are used to create whispering galleries. A person whispering at one focus can be heard across the room by a person at the other focus. Okay, again, all that sound, all right, doesn't have to be loud. They can be whispering at one focus, but that sound is going to bounce off the edge and be aimed right at the other focus. So if a person's standing there, they'll hear it. Okay. An ellipsoid is part of the design of the Texas State Capitol. A hand clap made in the center of the main vestibule at one focus of the ellipsoid bounces off the inner elliptical dome, passes through the other focus, bounces off the dome a second time, and returns to the person as an echo. So if you're standing here at focus 1, you clap your hands, okay? That sound's going to bounce off here to here, and it's going to then from focus 2 bounce back to you. Okay, so you'd hear the echo of it. All right. First example here. This comes from our chapter opener. It says, if the ellipse of the White House is 616 feet long and 528 feet wide, what is its equation? Now they have given us a picture, and based on this picture, would our major axis be horizontal or vertical? Based on our picture. Horizontal, right? They're showing us a longer dimension in the horizontal direction. Okay. Now, if they hadn't told us that, if they just said the major axis is 616 feet long, you wouldn't be able to tell. Is it Are they referring to it being horizontal or vertical? So in that case, I would accept either version of our equation, okay? But based on the picture they're showing us, it does look like the major axis is horizontal, okay? So we're going to base it off of that. So our major axis is 616 feet long. That is what length in terms of variables? The major axis from vertex to vertex is 2a, right? Because from center out to a vertex from either direction would be a units. So they're really telling us that 2a is 616, which means a has to be 308. Okay. And then for the minor axis, we're told it's 528. That's equivalent to what? 2 b's from covertex to covertex. So 2 b's is 528, which means b has to be what? Okay. And we said that our a is going in the x direction, horizontal. So b is going in the y direction. Is that enough to write our equation? Yeah, they didn't say anything about finding foci or anything. We don't really need to figure out C at all. Okay. Where would the center be? Yeah, if you have the option of placing that on a coordinate grid, why wouldn't you put it at the origin? Right? You don't need to create a more complicated equation than needed. So we are going to assume our center is being placed at 0, 0. Okay? So we have a basic equation. X squared over something plus y squared over something equals 1. What's going to go under the x squared piece? $308 squared, right? And for this, I'm going to let you just leave it like that, 308 squared. You will need your calculators for the next one, though, so if you've grabbed it, that's great. And then what goes under the y squared? 264 squared. Okay? Questions on that one? All right. Our last piece is another application. It says, ellipsoids are used in healthcare to avoid surgery in the treatment of kidney stones. An elliptical lithotripter emits underwater ultra-high frequency shock waves from one focus with the patient's kidney carefully positioned at the other focus. Okay, so the shock waves are all coming from here. They're going to bounce off the edge and be directed at that kidney, okay, to break up the kidney stone. The ellipse used to generate the ellipsoid of a lithotripter has a major axis of 12 feet and a minor axis of 5 feet. How far from the center are the foci? Did they ask me to write an equation? No. So it doesn't matter if our horizontal axis is vertical or, if our major axis is vertical or horizontal, right? It doesn't matter. They're just asking us to locate where the foci should be. Okay? So we really need to find what? We need to find C. So I'm going to pause the video. At your tables, I want you guys to go ahead and find C based on the information you're given. All right, let's see what you did. What was your first step? Finding A and B. Okay, so how did we figure out A? Okay, so 2A was 12. A has to be 6. Okay, and then they said 2B was 5, so B was 2.5. Okay, then what'd you do? C squared equals A squared minus B squared. So C is the square root of that? Yes? So we need the square root of 6 squared minus 2.5 squared. What did that come out to be? 5.454? Okay, and this was all measured in feet. So what we would say is that the foci should be located 5.454 feet from the center along the major axis. Okay? And we don't have to define whether that's vertical or horizontal. All right, we just are saying it's 5.45 feet from that center point. Okay? All right, so we have learned so far, we did a quick review of circles, right, that we had done way back first semester sometime. And then we spent a few days on parabolas. And now we've just spent a few days on ellipses. Okay? Tomorrow we start our last conic section, that's the hyperbola. So make sure you take some time and really get what are circles, what do those equations look like, what are the key features. What's a parabola look like, what are the equations for that, what are the key features of that. Same for an ellipse, okay, before we add in our fourth one. I was almost thinking we were done. We got one more.
We don't have to do it.
Oh, we do, because this one's fun.
When you say it's fun, it's actually fun.
It is. Let's do this one more, and then we'll get the assignment up there. Okay. The moon travels about the Earth in an elliptical orbit with the Earth at one focus. The major axis has a length of 768,806 kilometers, and the minor axis has a length of 746 kilometers. Find the greatest and least distances from the Earth's center to the moon's center. Okay, so we're picturing this moon orbiting around here on that ellipse. Okay, Earth is centered at this focus on the left. If the moon is here, it's going to be the farthest away from the Earth that it can be. Okay, if the moon is over here, it's going to be the closest to the Earth that it can be. All right, so farthest is this distance. Closest would be here. Now, I want you to think in terms of that major axis. Going from the two locations that I said the moon could be in, those would be your vertices, yes? Middle point here is our center. And we have the Earth located here at a focus. Yes? Let's label these with our A, B's, and C's. So from the center to the vertex, this much is, what letter is that? Center to vertex. That's A. Okay? To go from the center to a focus is C. So this whole distance from where the Earth is at a focus all the way to the farthest point over, this whole thing here is A plus C. Okay? So to find how far they are at the farthest point, we need to figure out A plus C. To find the shorter distance, which we said was this, what would we have to do? A minus C. Because from center out to this far vertex here is A. We've already used up from here to here a C value. So our shorter distance here is going to be A minus C. Okay? So are we given information where we can find A and C? Yes. All right. We are told major axis is 768,806 kilometers. What do we have to do to that? Divide it in half to get A, yes? So 2A is 768,806. What would A be? 384,403. Okay? And then 2B's was our minor axis. If we cut that in half, what do we get for the value of B? 383. Then what? Yes? Okay. How do we find C? A squared minus B squared and then square root it. Yes? Okay, we're going to have some really big numbers here. So grab your calculators. Figure out A squared minus B squared and square root that. Because we're dealing with such large distances, let's go ahead and round it to a whole number. What would it round to for C? 20,000. What is it? Are we agreeing with that? Okay. All right, so our farthest apart, we said was A plus C. What do we get if we add A and C together? If we add A and C together, what do we get? Did you say 479 or 179? That's what I had too. Let's fix that. I maybe just misheard you. Okay, so we're adding A and C, and we get 404,582 kilometers. And then the closest we said was A minus C. What do we get for that? Oops, 364. Agree? Okay. Now you can get to your homework assignment. All right, you guys are working on day 2. I did put a comment on here about there's going to be some questions asking you to find the eccentricity or the E value. You can ignore that. We're not going to do that part. Okay?